A stack implemented with the linked list was our first example of a recursive, that is, self-referential data structure. In this presentation, we will explore recursive control structures. Let's begin with some of the fundamental principles of recursion. Any problem that can be solved with iteration can be solved with recursion. The converse is true as well. Any problem that can be solved with recursion can also be solved with iteration. In much the same way that it is possible to create an infinite loop with iteration, infinite recursion is also possible. Because computers have finite memory, it is not actually infinite, however. What happens instead is that the compiler's runtime stack will overflow and the program will terminate instead. All recursive solutions must have at least one base case and one recursive case. A base case is what is needed to ensure that the recursion will terminate. Iteration is an imperative approach to solving problems that require repetition. By contrast, recursion can be thought of as the first step towards declarative programming. Recursive solutions involve creating a recursive definition rather than an algorithm, which is what an iterative solution requires. To understand recursion, it is helpful to look at some examples. Creating the sequence of Fibonacci numbers is a classic first example of recursion. In this sequence, the first two numbers are 0 and 1, and each subsequent number is the sum of the two previous ones, which is a recursive definition. Although possible, it is difficult to define this sequence iteratively. The iterative definition involves powers of the golden ratio, an irrational number whose definition contains the square root of 5, and whose value is about 1.618. We have already given a recursive definition in English, but it can also be expressed in a more formal mathematical fashion. Notice that the definition involves two base cases, when n is 0 and n is 1, and a recursive case in which the sequence is defined in terms of the previous elements in the sequence. To see some of the benefits and drawbacks of recursion, we will compare several versions beginning with the iterative approach. The method signature of all versions of this method state that it is supplied a parameter that specifies which number in the sequence we are requesting, and it returns that element of the sequence. We designated this version as Fibonacci 1. It requires three local variables that form a three-element window across the sequence. Initializing these variables properly is essential to ensure the correct result in the base cases. This loop iterates n times. The loop control variable I is just a counter and never used in the loop. Ensuring that the loop goes from 1 to n is still important, given how we initialize the two local variables. The variable counter is an instance variable of the class. It plays no role in the computation, but we included it as a way to compare the performance of different versions. This is the line in which we compute the next number as the sum of the two previous. In these two lines, we move the window forward one position. The order of these two assignments is critical. On the next slide, we will show an animation of this portion to make clear what is happening. After the loop completes, we return the result. It should not be immediately obvious why previous is what needs to be returned. The iterative version requires careful testing. To see that this method produces the correct result, we must examine what happens when n is 0, 1, and then all numbers beyond. When n is 0, the loop never iterates, so previous remains 0 and 0 is returned. When n is 1, the loop iterates once, so previous is set to current, which was initialized to 1, and 1 is returned. So both base cases work correctly. When n is 2, the loop iterates twice. The first time through, next is set to 0 plus 1, which is 1, and current is set to next, so current becomes 1. The second time through, previous is set to current, so previous is 1, which is returned. Without that careful analysis, we could not be certain that this method was correct. To better understand the critical 3 assignments inside the loop, let's watch an animation. Previous and current were initialized as 0 respectively, so this is the initial state. The first assignment in this sequence computes the next element, so now these 3 variables form a 3-element window. Then previous is set to current, and the window collapses to 2 elements. Next, current is set to next. The order of these assignments is very important. When we go around the next time, next is computed and the 3-element window is reconstructed. Notice how much careful testing and examination of the loop body was needed to understand how this relatively short method executes. Now let's look at the recursive version and make some comparisons. This if statement covers both base cases. It returns 0 when n is 0 and 1 when n is 1. It returns the sum of the 2 previous otherwise. Notice that this method is calling itself. That's what makes it recursive. It is actually doubly recursive because it calls itself twice. To be more precise, we should say that it calls another activation of itself, because each activation contains a different parameter n that contains different values. What is good about this version is that it is much shorter. It has fewer lines of code, and no local variables. It also requires no real testing, because it is just a restatement of the recursive definition. There is one disadvantage, however, which is that it is very inefficient. We can see why that is the case by looking at the activation tree with n equal to 5. Each node of this tree represents one activation of the method. The number inside the circle is the value of n passed in, and the number above the value returned. The problem with this approach is that the same values are computed repeatedly. Notice in particular how many times the method is called with n equal to 1. The amount of time required is proportional to the number of nodes in this tree, which grows exponentially. It is important to understand that although recursion can simplify problems, such solutions can be inefficient if we're not careful. Let's examine the efficiency of both versions as well as 2 additional ones. The iterative version, Fibonacci 1, contained a loop from 1 to n, and we've already observed that such behavior is linear, or in big O terms, O of n. The activation tree that we just examined revealed that the recursive version, Fibonacci 2, grows exponentially. The base of the exponent is the golden ratio mentioned earlier. Solutions that grow exponentially are unusable when n becomes very large. To illustrate that not all recursive implementations are inefficient, we have included 2 more versions. We will forego a detailed line-by-line explanation, but we encourage you to study the code provided. Instead, we briefly explain how these implementations differ. The Fibonacci 3 version consists of 2 methods of the same name. The one with the matching signature is the starter method, which calls the recursive one. The recursive method accepts a pair of parameters, previous and current. It is singly recursive and also tail recursive because the last line is the recursive call. Being singly tail recursive, it behaves much like the iterative version, so it is linear. The fourth version, Fibonacci 4, uses a technique called dynamic programming. It looks very similar to the first recursive method, except it saves the values in an array list as it computes them. This saving of values is often referred to as memoization. Before attempting to compute one, it checks whether it is in the array list. If it is, it just retrieves it. Because values are only computed once, it executes in a linear fashion. So now let's run this program and look at the relative behavior of the various versions. And we're going to, let's enter 10 for example. And what's important to notice here is that in every case we got the same result, which was 55. However, the counters were very different. And in all but the second case, they were linear. In this particular case, perhaps we would refer to it as 2n, maybe in this case n plus 1, but that's still n. But notice how big it was in the case where we had the straightforward recursion. So that was the one that was very, very inefficient.